No. No, you may not. I mean, yes, you can, but I won't listen. I may not listen. What's your request? Okay, Daniel, we have homework 12. It's going to be due Thursday. And then homework 13, you'll turn in on our test day next Tuesday. Okay. That stuff will be on the test, so I'll probably do what I did last time. Yeah. So test 4 will be the 23rd, and then 30th is your final. Okay. Okay. So we are going to pick up on page 22 in our note packet right now. We are going to do some more regular expressions from these machines, and then we're going to hopefully start some counting stuff today. Yeah. And some probability things. Okay. So as soon as this gets on, I will do that. Okay. Well, somebody talked to me about what kinds of things would be accepted by this finite state automata. Mm-hmm. What strings would be accepted? Yeah, what strings go to a final state? 0, 0, 0, 0, 1, 0, 1. So the 0, 0 is happening to get us from S0 to S1 and S1 to S2, which is final state. So just 0, 0 works, yeah? But then after that, you can do 0 or 1 and stay in S2. Yeah. So the idea here is that you could do 0, 0, and then you can do 0 or 1 star. So this is 2 zeros followed by any number of zeros and ones. Yeah. No. Sometimes the complexity means that it's not right. I can't think of a way you would do this correctly in a different way. I guess you could do like 0, 0 or 0, 0, 0 or 1 star. Yeah, no, that's fine. That's fine. Yeah, I'm not gonna like I am gonna just do yeah, if it works, right? Yeah. I don't care if it's the most efficient route. Okay, so this is actually probably the hardest part of this. I say that, but I don't know if that's true. Where you have these strings that are accepted, and you have to draw the machines. Yeah. So on this one, we have 0, 0, X, where X is any string. So our alphabet here, we should know, is just zeros and ones. So this is 0, 0, and then any string of zeros and ones. It's the thing we just looked at. Are y'all with me on that? So you start at S0, you go to S1, you go to S2, you have 0, 0, and then X is any string, so it could be the empty string. So we can do this as a final state. And then we can stay in here with zeros or one. Now, the problem is that I don't have the outputs of one coming out of S0 or S1. So I'm going to just like make a trash place and make that S3. Yes, that's what I just said.
We have to have at least one input, or at least, or yeah, we have to have both the input coming off.
Yep, they got to go somewhere, even if it's to the trash, right? Every state has to have, it's going to take in both inputs, so they have to come out somehow. But they're not accepted, so they're not going to always go to the final state. They're just going to go somewhere. Oh, sorry. Yeah, sure. Yes, it does. Zeros and ones here staying in the trash once you get there.
So if it just dumps all the ones, would it just stay there? No output from it?
Yeah, but S3 has to have, you have to have those outputs for S3 as well. So you're just going to keep them there.
Okay.
Once a one happens, if a one happens before those two zeros, then it's just going to go to the trash. And no matter what happens after that, it's going to stay in the trash. All right. And then for L, we have the string is x00y, where x and y are any strings of zeros and ones. Still, our language, our alphabet is 0 and 1. Well, at least part of it's going to look similar to what we just did, right? So I'm going to go ahead and that'll be all right. Okay, so we got to figure out how to deal with that X in the front of those two zeros. So like if we look at the string, I don't know, 1 1 0 0 0 1. That fits this, right? How do we make our machine accept that and take it from an initial state to a final state? Okay, so if we make 1 go back into itself here, we could do 1 1 0 0 0 1, right? Okay, but what if I made this go back here if the 1 popped up then? You said you can't do 1 0 1 0 0 1, right? But now you can, right? Yeah, so the 1 1 0 0 0 1, good. 1 0 1 0 0 1. Yeah. And everything has a 0 and a 1 coming out of it. So I think that's done. This is where we start. This is S0, we'll say S1 and S2. Any questions about that on number 7? Yes. X and Y here are any strings of zeros and ones. 1 1 1 1. Yeah. Mm-hmm. It's going to be any. That's a way for like a placeholder for any string of zeros. Yeah. Well, because you can always come out of the garbage if you do it with 2 zeros in a row. You don't want a place that you go and get stuck, right? So if you put in like 1 0 1 0 1 0 1 0, right? You would do 1 0 1 0 1 0, whatever, right? But you're never going to get to that final state. So it's, in essence, it's the trash. But you could get out of the trash if you put 2 zeros. Like if I threw this on here, right? Then I'm out of the trash. And I could do you know, 1, 0, 1, 0, 1, 0, 0.
Right. It's kind of like a loop.
Sure. Yeah. And that loop, if you don't hit that threshold where you have 2 zeros in a row, you're gonna be stuck in that loop. You can come out of that loop and exit the trash if you can get 2 zeros in a row. Okay. Do you have questions about number 7? Number 8 is the language consisting of all strings that do not contain 2 consecutive zeros. That do not contain 2 consecutive zeros. As long as there are not 2 zeros in a row, we're done. We're good. That means that this, if you start with a 1, is a final state, right? I don't know. I should let y'all tell me how to do this. I'm looking at the answer, so I'm not giving you time to think. If 2 zeros appear, we're in the trash, right? Yeah. If just 1 0 appears, we're fine. Yes. And so we would, whatever this would be, let's call it S1. And then we could follow that with a 1, and be fine, right? And a 1, 1, 1, 1, 1, 1. Yeah. That's gonna get us stuck in a minute, I think. Okay. But this should also be a final state, right? So what happens then is you have if you get those 2 zeros in a row, we're going to end up in the trash. So we're going to just mark this guy as our trash pile in S2. 2. And we're going to stay there once we're there, because once you got there, that string, any string that got there, will still have 2 consecutive zeros. So we're going to stay in the trash once we're there. Now, if I start with a 1, that's fine, because that's a string that doesn't have 2 consecutive zeros, right? Or if I do 1, 1, 1, 1, 1, 1, 1, 1, 1, that's fine. So I'm going to start there and stay there if I'm looping with a 1. If I leave with a 0, that's fine. I can come back with a 1, but if I get that second 0 in a row, I'm in trouble. This is it. Are you guys okay with this or no? Yeah. Have any questions about number 8? You can't, because any string, that's what I was just saying, any string, like, who cares what's happening after here? If those 2 zeros appeared, that string, it belongs in the trash because it has 2 zeros in it, and you can't get it out. Right. Because if it comes out, it's got 2 zeros in it, and it can't be out, right? You've got to pick a different string. That string's trashed. Yep. How are we doing? Okay. Number 9 here, this is the language consisting of a set of all strings that end with 3 1s. All right, I'm gonna go ahead and make that a circle for me. There we go. Okay, you say to make this a final state. Well, I don't know what to call it yet. Just don't know how many I might have. We stayed in here. Because it has to end in 3 1s, it needs to have a 1, just a 1. And that zero will go out of it where? Yeah, if you, as long as you have at least 3 ones to end with, right? You could have more than that, so that's what kind of. Looping zero here, okay? No, because as soon as 3 ones appear, like, because none of those strings are unsalvageable, right? So you wouldn't go to the trash and stay in the trash. If you go to the trash, you got to have a way to come out and get those 3 ones in a row. Yeah. If you made like an S4 or something, you would have a 1 that would come out maybe and go here. And then you would have those 2 ones. Does that make sense? So like you could, yes, but you just got to do it in a way that still accounts for the ability to come back out of the trash. So if a 0 pops up, you got to start over to hope that you can get 3 ones in a row. And anytime a 0 pops up, you got to go back to the beginning and see if you can get those 3 ones in a row. Yeah, to end the thing. Yep. Every state has to have both of the like blank alphabet thing or all of the alphabet things coming out of it, going somewhere.
In this, you could, in here, you have like one, one, zero, zero, zero.
1 1 1.
One, one, one.
Yeah, right. You could have 1 1 blast. There's a 0, and then you would have 1 1 1 and be done. But if a 0 it was 1 1 0 blast, you're back here and you haven't.
You have it.
Okay, what do you think? Fine. I believe this is the hardest part of these things. Reading one that's already made is like, oh yeah, I could probably do that. Making them takes, practice and especially like making them efficiently, but you don't have to do that. We'll talk about that in just a second. All right, so number 10 here, we have the language consisting of the set of all strings that contain at least 2 zeros. So at least 2 zeros, they don't have to be consecutive. I know I need at least 3 states, right? Does that make sense?
This one, if you
And once those 2 zeros have happened, any string of zeros and ones after that is fine. So you got the zeros and ones there in your final state happening.
get a one, get back.
Because the zeros don't have to be consecutive. I don't have to go back. I can just stay put and hope that another 0 will come up. Because they don't have to be consecutive. I just need 2 zeros to happen.
Okay.
So because they don't need to be consecutive zeros, I don't care. I don't have to start over. Because if that happened, Ruth, like I could do 1 0 1 0 or whatever, but that 2 zeros have happened and I'm not in a final state, right? So like I need my language to accept that string and it didn't, or my machine to accept that string and it didn't. Questions, comments? You could. You can absolutely get stuck in an infinite loop.
So we don't like infinite.
The no, it is efficient. It is efficient, right? Your strings are not they're not infinitely long. They're all finite strings.
Oh.
Correct. It would that whatever the string is that is finite of finite length It's just not going to get to a final state. Your machine's going to deal with it, and then it's going to ignore it as useless. But it's got to run through this like process to see, does it hit a final state? No, okay, I got it. I don't need to deal with it. The like infinite loop thing here is that these strings are, in theory, there are finitely many of them, and so they're not, your machine's not going to run forever. They are of finite length also. The like, remember the like Claney star thing? It's that it's that thing finitely many times, including no times. But the fact that it's finite is, sort of how your machine is not gonna like break your computer. Does that make sense? And like you're right, you can get stuck, you could stay here, but like because again it's a finite length, it's gonna individually.
After like, it would be like, in that.
Basically the way that I think about this, and like I'm not a programmer, so like would take this with a grain of salt, but like you have a dialog box that pops up for your user to give write your name with a capital letter, right? And your machine, the thing you designed is looking for the first letter to be capitalized, or it's like first name, middle initial, last name, right? That's what you're asking for. And the person doing the input has put their first name and last name, no middle name, or their first name, their middle name, and their last name. So they're not following the directions. So your machine's going to say something like, no, nope, that's not what we were asking for. Follow the directions, right? I wanted 2 zeros in a row or whatever, right? So it's not going to do, the machine's not going to do whatever it was supposed to do because this string doesn't fit the criteria. Does that make sense? Okay. All right. Right. And like this would, in theory, it would end, but it's going to accept anything that ends in a one or whatever, right? So like, right, yeah. There are finitely many different strings that would be accepted in this language or not. Countably, maybe no, just we'll go fine. Okay. So we were talking about efficiencies and like, oh, am I going to judge you if you're, am I going to judge you? And by that, I mean, grade you more harshly if your machine is inefficient. And the answer is no. I'll probably draw it efficiently for you, but no, I will not penalize you for that. But I want to look at these two machines here. These are actually, they're not the same machine, but they do the same thing. And that's so the thing about this is like maybe the house one is easier for you to understand, and that's fine. And that would be like the job that you have sometime is to clean up a program. Like, oh, there's some inefficiencies here. I can make this better and more streamlined. And you would produce. Your job would be to produce Finite Say Automata number 2, right? So again, I know nothing about computer programming. This is just me speaking about what I think happens in the world of computer programming. I don't know what you do. Okay. So for you for the spring or me, maybe I should sit in on the class. Okay. Audit a class. So let's look at the language or the strings that would be recognized under this machine. So let's do the route where you start with a 1 first. So like it's just a 1. Just a 1. Right? If you go this way, you end in this final state. But if you have anything else, you come out of it and you're toast because you gotta go stay in this trash and stay there forever, right? So just if you go this route, only a 1. If you go south here instead, what happens? Oh, you can do a 0, and then you can do a 0 star, right? And then you can do a 1. And if I have anything else that happens after that 1, I'll leave my final state and go into this trash pile over here that is S3, and I don't want to be there. Yeah. So these are this is it. And so you would write this if you were doing this on a test. I imagine you would do this 1, or I gotta make my but my OR bar is really big because the ones next to the OR bars is really hard for me to, yeah. So this would be your like the thing you would write for the language that this machine accepts. Yeah. Regular expression stuff here. Okay. But then let's look at this one down. Yes, you can. This is the whole point. I'm trying to make the point, Charlotte. I said that. Yes, this is not the most efficient machine. Is it wrong? No. Does it do what we wanted it to? Sure. Yeah. But our job, maybe as computer programmers someday, would be, can I make this better? And the answer is yes, right? So on this one, you can see that you can do 0 star 1. And that's it. And if you really think about it, that's the same thing, isn't it? If I choose to have no zeros in this star, right? That's fine. I would put me with this guy, right? If I choose to have 1, well, then I'm over here on this side. And that's fine. Yeah. So either one of those is fine. I don't know which one you would come up with if I gave you like, I don't know. If I gave you this thing as to draw a machine that accepts these strings or whatever, right? I don't know which of these you would come up with, and it doesn't matter to me, right? And sometimes you come up with an inefficient one, and then you think about it, and you're like, I could do better. Right? So, okay, so these two finite state automata are equivalent. They're not the same machine, but they do equivalent things, right? So they are equivalent because they recognize the same language. Good? All right. Any questions about 12.1 or 12.2? No? Ready to do some counting? Yes. 6, 7, 8. I thought you were a volleyball coach, not a dance coach. Okay. I liked it, though. What just happened? Oh. Yeah. Okay. Good. Good.
I got it.
Oh. Whew. I've never actually seen that happen on Sesame Street. That's Sesame Street, right? But my husband does it sometimes, but you don't sound the same way that he does, and that's my only like. No, you're not. No, he's very aggressive. My husband. You know. Okay, so we are going to do some counting stuff here. This is the last 9. I don't remember how many sections of chapter 9 we have. 3? 9, 1, 9, 2, 9, 3. Okay.
9, 1, 9, 2.
9, 5. 9, 1, 9, 3, 9, 5. Ruth, we do 2 also. Okay, whatever. Counting. So we're tossing 2 coins. How many heads are showing?
1 out of 2.
I tossed 2 coins. How many heads are showing?
None.
Thank you, Logan. 0, 1, or 2. Good job, Logan. This is a sample space. It's a set of all possible outcomes of a random process or experiment. An event is a subset of a sample space. So the event of getting 1 head showing is an outcome of that sample space. We good? No, it could be like the event could be that you get 1 or 2 heads. Yeah. Okay. So if S is a finite sample space in which all outcomes are equally likely, and E is an event in S, then the probability of E, denoted P of E, is the number of things in the event divided by the number of things in the space. So this is the number of outcomes in E divided by the number of outcomes in S. remember N of A, that's the cardinality of a set. I don't know if you remember that or not, but that's cardinality. Those like absolute value bars around a set is how many things are in the set. So N of A means the same thing. Okay. Now this is a part of the class that I always am concerned about. Like, do you know what playing cards are like? Okay, this is the best way to talk about statistics, but then like people are like, I don't know how many suits there are. I don't know how to help you. Go look at a deck of cards. Marina, are cards a thing? No, that you're familiar with? Yeah, I'll do my best to ask you questions that don't have anything to do with playing cards. All right. Have I told y'all about this one time? This is funny. This is fun. This is a good aside for you. Are you ready? This one time I had she was an international student. I don't remember where she was from. It doesn't matter. But the question was about a baseball diamond. And it says like this is a baseball diamond. It's a square, but it's a baseball diamond, right? So it's a square, just right. Right. It's the like thing said. It says a baseball diamond, which is a square, right? And it gave like the distance between each of the plates or the bases, right? And I went over to help her, and she had the most oblong rectangle drawn on her paper, and I was like, what are you doing? And she was like, I don't know what a baseball diamond is. Well, it's not a rectangle. It says it in the problem. What are she was like, I guess she's drawing like cricket. I don't know. Maybe she was from London. I don't know. But I was like, it says, if this is not a knowledge about baseball thing, this is a reading comprehension thing. It says it's a square. But that'd be good. No, she drew a rectangle. Y'all, it took up the width of the paper. Like, what are you doing? I say this to you, and you're like, oh my gosh, is she talking about a student behind her back? No, I laugh at her in her face too. So it's okay. She knows that I thought it was hysterical. Okay. So a standard deck of playing cards, what's the probability of drawing a black face card at random? We gotta do all of this. So the probability of the event, remember, is going to be the number of black face cards. And we're going to divide that by the number of cards in total. So a standard deck of cards is 52 of them. Face cards are Jack, Queen, and King. There are 2 suits that are black. So this would be 6 out of 15. Jack, the Queen, and the King of Clubs. And the Jack, the Queen, and the King of Spades. Oh, I don't care at all. I'm not going to have a calculator for this. I'm not going to expect that you do either, but when you do your web assigned stuff, you're going to have to do whatever it tells you. It'll tell you in its wet. Okay, what's the probability that when rolling a pair of dice, the sum of the numbers showing is 6? It's actually not 1 out of 6. Huh?
Oh, pairs. 2 out of.
Nope.
2 out of 12.
What are the ways that we could get a 6 with 2 die? 2 and 4, 3 and 3, 1 and 5, 5 and 1, 4 and 2. 3 and 3 doesn't matter because they're both 3, so the order of that one doesn't matter. But die 1 is a 3, right? Die 2 is a 3. That's the same as die 2 being a 3 and die 1 being a 3. So you don't have to count this one twice. But you do have to count this because this is die 1. This is die 1, right? Yes?
If it's the same color.
But the die are separate, right? So you roll one die, you roll the other die. Yes? So it's the ways that this could happen is die one is a 1 and die two is a 5. Die one is a 5 and die two is a 1. Right? So that's two different ways that it can happen. But die one being a 3 and die two being a 3, there's not two ways that happens like this. Does that make sense? Or no? Oh, I'm ready. You ready? PV is going to be the number of ways to get a 6. Divided by the number of pairs. Ooh, that's tricky. How many pairs of dice are there? You've got, I'm going to teach you how to count these in a minute. How many things could go in this first, for this first die? And how many things could go for the second die? Also 6, so that's 36 down. Because they're both happening. And then this is 5 of those 36. We have 1, 2, 3, 4, 5. Yes. Yes. Six squared, yeah. That there are 6 numbers that could go for that first die and 6 numbers that could go for that second die.
Oh,
Yes, it's a cube. With numbers on each face. This is fun. How fun. This will be on that, some of this will be on your computer science exam too. I don't know if you guys have to take that, those of you who are cybersecurity. Okay. What's the probability that a randomly chosen 3-digit integer is divisible by 5? You in just a moment. Okay, so it's a 3-digit integer, yes? I don't care what's in either of these two spots. Right? Because what makes the thing divisible by 5? This being a 0 or a 5, right? Yeah. Okay. How many things could be in that spot? Because of 0, right? 0 through 9. So there are 10 options for what could go in that third digit. 2 of them would make it divisible by 5. So the probability here is 1/5. The so 2 options here would make this divisible by 5. There are 10 total numbers that could go in that blank. Right? Because it's a 3-digit number, so that third digit could be 0 through 9. Yeah.
Oh,
right.
now I see.
The third.
I was thinking like
yeah.
any integer times any.
No, sorry. This is a
That's
3.
why,
No,
right.
this is a 3-digit number.
Okay.
There are 10 options for that third blank. 2 of them would make it that 3-digit number divisible by 5. So 2 out of 10 would be divisible by 5. So 1/5. We good? Yes?
Yeah.
Okay. This is a weird thing that's going to happen right now, but what just happened, and Whitney just did this too, that there are actually 10, not 9 there, because you're going to do if m and n are integers, because you got to count one of the steps that you're on, m is less than n, then there are n minus m plus 1 integers from m to n. For our example we just did, we look at 9, well, not 90. We're looking at 9 minus 0 plus 1 to get the 10. Right, so 0 to 9. Then there are actually 10 integers between those. Okay, good. Just like make sure you're accounting for the step that you take to get off the initial one, right? If you just do 9 minus 0 there, you get 9, but there's one extra step there. You gotta add 1. Okay, are we good? You, it's that, because you're gonna be counting how many options there could be. So being like, if you're going from this range of numbers, how many things happen in that range of numbers? You gotta do the, n minus the beginning plus one. Okay, so we now are gonna look at the probability tree, and then we're gonna look at a multiplication rule. Huh? Yeah, right. Possibility tree. We've been talking about probability, sorry. Okay.
I read that as probability too.
We're all glad that Libby's here to help us read. Okay, so teams A and B are going to play each other repeatedly until one team wins 2 games in a row, or a total of 3 games. What is the probability that 5 games are needed to determine the tournament win? It's fun. Are you ready? Yes. Yes. Ready? Good. Great. I'm going to start with game 1. Yeah? What are the possibilities here? That team A wins, or team B wins. What? Should we just stick with, let's follow the road with A first. Okay. So game 1 has happened, A won. We're ready for game 2. What are the possibilities? A wins, or A loses, B wins. Right? Now, what is true about that very top thing? That's the end of that branch of, yeah, is it? That's the end there because A won 2 games in a row. Yeah? Okay. So if B won that second game, though, then A or B could win the third one. Yeah, I know. Now, what's true here? That's the end of this branch. It's not the end of the other one. Right? B did win 2 games in a row there, so we're done. But if it goes A, B, A, we're not done yet. Are you tracking that? Oh, yeah, no, I would not like it. So our possibilities here are that A wins or that B wins. This one.
Oh, for the C A branch.
Yeah, but you don't think about, because winning, if you won 2 games in a row, right? You don't think about that, right? Right. Right. So you would do 3 in a row or 5 total, right? But that's just too many options here. Right. Right. But if you won 3 in a row, you would win the tournament. Yeah. This is best out of. It's just not.
It'd be best on a 4.
Okay, but that's not good. Best of 4 minus 1. I don't know. No, because the first team to win a total of 3 games. Well, we haven't had one of those happen yet. We're on the branch where A1, B1, A1, B1. What happens here? A or B again. Yeah, because A would have at that point won 3 in a row, or 3 total, and B has won 2 in a row. So those are done. Correct. Yeah, I actually am gonna do that. Sorry about your lives there, Joel. I gotta adjust that first one maybe, but No, it's terrible. Darn it. I gotta give myself more space.
Flip it upside down, flip that, left, right. Do that.
Upside down and then
Then
left
flip.
to right.
Well, like, no, like, it's gotta be upside down.
I can't. I'm trying. It doesn't work. But wait, I'm gonna make this B bigger. No, I can't. I'm just gonna do it again. I'm just gonna do it again. Okay, this is me. I would tell my children we can do hard things, and then I'm like, nope, think about. I'm just gonna do it again. Yes, you have to do it. Why would you not have to do it? Right. Do you want to fail?
I don't know why we didn't go outside with it.
I don't know why either. I'm regretting all of my decisions, okay?
Mine's running into each other.
I'm just, doing this. I hope y'all are too. Did I do this right? What? Yes. Good. It's just the first one we could make look nice and pretty, but we ran out of space to do the second one. We should have done it vertically right here. Oh, oh well.
Yeah, like that, like straight down, yeah.
Next time. Yeah, that's a vine, maybe. I don't know.
We could do like a March Madness tournament. No, I mean like the base. Like, they come together and do something.
Oh, this is yeah, we should have. Oh well. Trunk.
Oh, trunk. I mean, trunk. I was
Okay.
confused.
We are to be answering the question, what's the probability that 5 games are needed to determine the tournament winner? So,
Holy.
how many ways can this tournament end? 10 ways that this tournament could end. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ways that the tournament could end. Yes? How many of those ways required 5 games? 2, 1/5. Woo! It's these 4, Charlotte. If I had lined my tree up better, you would be able to see them, off by themselves. But these 4 took 1, 2, 3, 4, 5 games. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. What? 4. Dang it! Sorry, Daniel. And I was so confident with you too. I'm really good at counting. Okay, 2/5. Woo! Good. Good, Charlotte. Good, Whitney. Thanks for telling me.
Good try. Can I get a
Great try. I think it was excellent. I was with you. You had me convinced. Okay. So, so if things don't happen like that, right? Where are you raising your hand, Logan? No. Okay. If things don't happen like that, but like in this situation, the step we're on is dependent on what just happened, right? Yeah. Whether or not our tree ends is dependent on the step that's just happened, right? But if we're in a situation where all of the things have to happen, then you don't do this kind of thing. I'll show you what to do. So the multiplication rule, if an operation consists of k steps and the number of steps isn't dependent on the previous step. Is not. That's what I said. That's not what I wrote. Lord. Sorry. It leaks. The number of steps is not dependent on the previous step.
I was like, what am I looking at? What is that? No offense, I can't really talk about it.
No, it's fine. You're sometimes capital letters, sometimes lowercase.
I should draw, if I don't have lines, I'll just like the range, like, start going down lines. You know, like, it goes up or down.
I go down.
And it gets worse.
So you have these K steps, right? So step K takes calling these steps sounds weird. Maybe these are options. Let's go with options. Sorry. That's what my daughter said when she tried to run over me with her Jeep. Sorry. Oh, it doesn't really matter. Sorry. Okay. So we have if an operation consists of K steps, the number of steps isn't dependent on the previous step. So you got step 1, there are N1 options, step 2, N2 options, blah, 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 blah. Then the entire operation, you're going to multiply all of those things. So it happens in N1 times N2 times N3 times ... times NK ways. That's cool. I'm going to help you. Don't worry about this. Sure. Don't worry about this. Look, watch. I am a person.
Oh, wonderful.
And I, as a person, hi, Alessandro. I, as a person, sure. Do you want to pass the test with me? I don't know yet. I am going to order some coffee. Okay? Right? Surprise. It's not. I have some options, and the options are the same every time and not really dependent on the other options, right? Yes? So, I mean, your Starbucks person wants you to tell them in an order if you want the hot cup or a cold cup. And then it's, do you want decaf or regular, right? Okay, so we're going to do this. Are you ready?
I messed up my first.
So, I don't know. Normally, half cap Americano if it's in the afternoon. Venti. No. A venti half cap Americano iced with 2 pumps of caramel and light splash of half cap. What does she get? Just black coffee. It's espresso and water. So it's different. Extremely. So do you want my options to be regular decaf, or do you want the first option to be hot or cold?
Hot or cold?
Whitney, it's the choice. This is the choice that matters. Here I am. What? Sorry. So my person, hi Bryson, my person is gonna order me. I'm gonna order hot or iced coffee. Yes, and then here, yeah, and then I have to decide: do I want regular calf? No. Regular calf, half calf, or decaf?
What if we went with ice?
regular calf. I have options. Half calf or decaf. Oh yeah.
No,
I
still
want a
get
venti
20.
drink because I know the ratios for a venti drink, but I can't handle 4 shots of espresso at 3 o'clock in the afternoon and still go to sleep.
I like that. What's the point of decaf?
If you're pregnant and you can't have caffeine, but you like to taste the coffee and you want to fake it till you make it. You have ADHD and caffeine makes you crash really hard.
Or
Yeah. Ooh, a nice coffee after a meal, delicious. But in the evening time, you gotta be able to sleep. Can't have caffeine.
I have
An
caffeine, I
affogato.
don't
Is that what
care.
that's called? Okay, ready?
No.
Oh gosh, ouch! I hit myself with my Apple Pencil there. Okay, so hot or ice, and then I have to decide: do I want regular half calf or decaf? And then I have to decide: do I want a latte? Do I want coffee or do I want espresso? Let's go with that. Are you ready? So we got coffee, espresso, coffee, espresso, coffee, espresso, coffee, espresso, coffee, espresso, coffee, espresso. So
Maybe that's Christian.
on my first step, Christian who?
The guy that works Java.
What's his last name? Do you know? Okay. I may or may not know him. Okay, so at my first step, y'all, which is independent of the other choices that I made, how many choices did I have? At my second step, how many choices, independent of what I chose to begin with, right? Half calf, decaf, or regular? 3. Oh Lord.
Oh my gosh, no.
I'm not choosing that.
I didn't say people get it, just it's there. It's to be done.
That third option, when people get a frozen hot chocolate, I'm like, is that not just milk cake? I don't understand what you're saying there. That just,
My brother does that.
I don't
Puts ice
understand.
cream.
At that third step where I was choosing if I wanted coffee or espresso, which I did not write down because I didn't want to. How many choices did I have? 2. So how many branches do I actually have in this thing? This 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Woo! Now we actually did do that right, so we can celebrate. Woo! Do you guys ever wonder? This may be before your time, but Sonic at one point was like, we're America's drink stop. And he was like, could have this many combinations of drink. Yes, they did this thing. But you do this thing where they're all independent of one another, so that number grows like a lot. But you're not really going to put some of those things together. Right? Yeah. Yeah. Do you know where those numbers came from? 2 options at the first step. I got to decide, do I want my barista to grab a cold cup or a hot cup? We should have gone sizes first. Darn it. This is step number 1. Logan's like, that's not what I meant at all.
I meant like and then you can draw all the way straight down.
Pretty options.
Close enough.
Okay, so I have those 3 steps. That first step, I have 2 options. That second step, I have 3. And that third step, oh shoot, 2 in there. Yeah. It's right there. It's tiny right there, 2. Yeah, because that one branch got really tall. Okay, so we have 2 times 3 times 2 ways that I different coffee orders that I could have based on these options. Yes, we good? Okay. How many things are, if I have has sets A, B, and C. A has D elements, B has N elements, C has M elements. How many elements are in the set A cross B cross C? Do you remember what that thing means? Way to go, Ruth. What does a Cartesian product look like? What are the things What are the elements in the set that is a Cartesian product? Ordered pairs, and in this case, ordered triples. Yes, X, Y, and Z. Great, good. Okay. So we have an ordered triple. Yeah. How many things could go in spot number 1? D many things. How many things could go in spot number 2? N many things. How many things can go in spot number 3? M. How many things are in this set? A cross B cross C. Good. Oh, I should use capital N. That was a product you said there, right, Whitney? D times N times M. I don't know. Seen some crazy stuff, y'all. All right, you ready to keep going? Yeah. We ready? Now we actually get to start counting. I'm gonna stop doing probability for a little while. Are you ready? Good. How many 4-symbol pins can be formed using the standard 26-letter alphabet and 10 digits? Repetition is allowed. D, 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 D. Mm-hmm. You want to explain yourself?
Yeah.
No.
You just shake your head and smile. Because there could be 36 letters worded in 4 to 5. Kind of like what we did with the T as a that.
So in WebAssign, you're not going to get to write 36 to the 4th. You're going to have to, yeah. Yep, by hand. Make sure you do it by hand. Show your work. Yep. I need you to start over, please.
So you know how we did the star?
The cleaning closure thing? Mm-hmm. Yep. Yep. It's not a connection I've ever thought about before, but that's good. Yes, truth. Mm-hmm. I like it. I just wasn't expecting it, and then I was totally lost. Okay, what if repetition is not allowed? Again, in WebAssign, you're actually going to have to do that by hand. I have no idea. Alessandra's going to figure it out.
1.69.
Just 7. Okay. What's the probability that a pin chosen at random has no repeated symbol? We're doing probability now. Yes. Yep. The number of things in the event divided by the number of things in the space, right? So this would be the number without repetition. And this is the total number down here. That includes repetition. So we're looking at 36 times 35 times 34 times 33 divided by 36 for that probability. Cool. What is it, Alessandra? different 1.6 million thing Daniel's trying to come up with. You're so sad. What's happening? Really?
It's harder when they're not like pairs. So I just did like 60. So it's harder with that.
You was right with the 1.6.
That seems high, right? Oh no, I believe you. I'm just, I'm not used to probability numbers being higher than, I don't know, 4. I do know a lot of things. I didn't know that this was 88%. No. Great. See? Right. I had no idea that I needed the 4%. See, I just made it happen. Okay. So a permutation is a set of objects that have an order. So if you create a list, this is a permutation. List. You're reordering objects or ordering objects. So order matters. We'll do some stuff Thursday where it doesn't. But let's say we have 5 objects. How many different lists of those 5 objects can we have? I want to arrange the 5 of us in a line. How many ways could I arrange that line? How many different lines are there? I don't know, make me do some math here, but no, I don't think so.
5.
Yes, Ruth, talk. Go.
5.
No. How many people could be in the first spot in the line?
5.
How many people could then be in the second spot?
5.
Good. Oh, my line got wonky. Yes, because we're people, right? So we're not going to repeat. We're going to be in one spot in the line. Once we appear in that one spot, we're not going to appear again. This is 5 factorial. What? Yeah. I knew it wasn't 25, but I was like, I can't math. Okay. For an integer n with n bigger than or equal to 1, the number of permutations of a set of n elements is n factorial. It was. You gotta read ahead. Yeah, you are. I'm not gonna do this, but yeah, you are. Maybe. Oh yeah, right. Because stats variables are made up. No. A combination, the order does not matter. So like a combination would be like the 5 of us together in a set. Just the 5 of us together. Which is, so there are more permutations of the 5 of us than there are combinations of 5 of us. Because like you would list us one. Right.
I always use the long way.
What the heck does that mean?
So they give us like 5 of us to be like,
Are you going to make the list? 120 people, 120 lists. You're going to write them all down. That would be the long way. Don't do that. Use this. Yeah.
you do have an extra hour on the file, but
Okay. In our permutation of a set of n elements, so we have like us, we're the number of people in this room would be the n elements, and I want to do a permutation of the 5 of us within that. Of 5 people within that, not just 5 of us. So we're looking at that. The number of R permutations of a set of n elements is denoted with P and R. You can do this in your calculators. If you hit the stats button, so when you're doing your web assigned stuff, you need to do this. but you are basically, what happens here is you have, I don't know why I'm choosing 36 and 4. Anybody know why I'm doing that?
Sure.
I know. So we have 36 symbols, and we're gonna use 4 of them to make a pin.
Is that what was
I
going
know,
on?
I know. I'm with you. I got it now. I just needed to catch up with myself here. So in that first spot, I have 36 things, and the second spot, I have 35 things that could happen, and the third, I have 34, and in the fourth, I have 33. So we're permuting 4 of those 36 elements, and repetition's not happening. So this is what we did on number 3. Yeah, something serious. Do y'all know that Dr. Probin's CSU thing is 3 digits?
What? How?
Like,
ID?
yeah, either his ID or the yeah. Oh yeah, this is your. I think this is 20 here.
So who's number 1?
What does that mean?
Like who's ID
Oh,
number 1?
they're probably dead.
Well, yeah, but like, who is it?
I don't know.
Well,
Maybe they started with 3 digits.
yeah, I think Automata probably.
Well, that's
There wasn't. Yeah, I don't know.
what is it stuff?
Right. Back then. Please tell Dr. Probin you said that.
No, not.
Oh, when Dr. Probin started, they didn't have technology.
I would love to see his face.
In the not man, no,
Sounds like my friend. It's not talking about a laptop.
Okay, so if n and r integers want 1 less than or equal to r, which is less than or equal to n, the number of r permutations of a set of n elements is given by p and r. Remember that thing, we just did this, but this is n factorial divided by n minus r factorial. If you think about what we just did p 36 4. So that is 36 factorial divided by 36 minus 4 factorial. 36 factorial, you know, is 36 times 35 times 34. Logan, what's up? Permute. Sorry. This would be what, 32 times 31 times 30. Dot, 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 dot. So like everything after here is going to cancel out, and it's those 4 things what we did before. Go. Wait, what is that? This is 36 minus 4 factorial, which is, yeah, sorry. This is 36 minus 4 factorial, which would be 32, 31, 30, blah, 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 all the way down. 36 factorial up on top. So the 32s and on are going to cancel. And you're left with 36 times 25 times 34 times 33 times 32. No, just 33. Stop it. And it's 3:20, and I'll see you guys on Thursday. Yay! Guys, only one more day of learning material in this class. There is a final exam review. Is that what you're about to ask me? It's in Blackboard, but I'll print it and give it to you on Thursday. There's no class before it, no, because it's a week. And then when I've done it in the past, having that class was useless. But I have some like resources for you from when I have had final review sessions I've gone through with my classes and those things. So I'll have some stuff for you.